Hello students, so in this lecture we shall be discussing about LS coupling or spin orbit coupling, and this is also called spin orbit coupling or RS coupling, that stands for Russell-Saunders coupling. Now, there are three perturbations in order. One is the spin-spin correlation. Let me put it as SS. Okay, spin-spin correlation. The next is the residual electrostatic interaction. And the last one is your spin orbit interaction. So all these perturbations are to be taken into account. Now, considering the first one, the spin-spin correlation, the individual angular momentum vectors of the optical electrons are strongly coupled with one another to form a resultant spin angular momentum. So there are a lot of, for example, a spin angular momentum will have a magnitude s into s plus 1 h plus is a constant of motion. Now this s value can take, considering large number of spins, the spin quantum numbers will vectorially add to a minimum and to a maximum. So the values of S will be the vectorial additions between the minimum and the maximum, all the possible values of S. Now the states with different S will have considerable energy difference, the one of the highest S being the lowest energy. So the highest S will have the lowest energy, and the different levels, and they will have different levels, and the number of levels will be 2s plus 1. It's called multiplicity. If for example, if there is only one electron, then the value of S will be half, since only one electron is present, so 2s plus 2s plus 1 will be equal to 2, and it's called a doublet. So it will have two different S values and corresponding two different energy levels. For two electrons, it will have S1 is equal to 1 by 2 and S2 is equal to 1 by 2, so they will vectorially add. So total S will be the maximum, and between the maximum and the minimum value, the maximum value between half plus half 1, and this is S max, and S min will be half minus half 0. So total S will be 0 and 1. So this Now in this case, the 2s plus 1 would be equal to 1, so it's called a singlet. And in this case, 2s plus 1 is equal to 3, so it would be called a triplet. So for 2 electrons, we get a singlet and a triplet, whereas for only 1 electron, we get a doublet. So we can continue with this. For 3 electrons as well. So for 3 electron system, we have S1 1 by 2, S2 1 by 2, and S3 1 by 2. So S will be, S max will be if we add 3 of them. So it is 3 by 2. And S min will be if we have 1 plus half minus half, so these two cancels out, we have 1 by 2. So S value will be 3 by 2 and 1 by 2, and for this case 2s plus 1 will be 4, and in this case 2s plus 1 will be 2. So we will have 2 sets of doublet and 1 set of quartet. So this is what is called a quartet, and this one is a doublet. Now the question is, we will get 1 set of quartet and 2 set of doublet, because this combination can also be written as equal to half minus half plus 1. So 2 sets of doublet. So in fact, there will be one more half corresponding to the different combination, different vectorial addition of this. So we get 2 sets of doublet and only 1 set of quartet in this case. Now the next is your residual electrostatic interaction. This is as a result of individual orbital angular momentum vectors of the electrons are strongly coupled one another to form resultant orbital angular momentum. So as in the case of the spin angular momentum vectorially adding with one another, here the orbital angular momentum will vectorially add with one another. And we know the magnitude of L is L into L plus 1 H cross. So again, it can have the, so we are talking here about the vectorial addition. So L again can take values between L min and L max, all the possible values it can take. And for L is equal to different values, L is equal to 0, 1, correct here. For L is equal to 0, 1, 2, 3, we will have different levels are designated as S, P, D, F, G, etc. This is for the electrostatic interaction. And the next third perturbation, as we have discussed, is your spin orbit interaction. So here we get a total angular momentum. Spin orbit interaction with the total angular momentum L, J is equal to L plus S. So here again we will have L minus S minimum to L minus S maximum values it can take. Now J will always, J is a half integral or half integral. The value of J will be integral or half integral. It will depend upon whether S is integral or not. If S is integral value, then the J will be integral. If it is not integral, then A will also be not integral. Now the number of J will be how many number of possible states angular momentum. This is the called total angular momentum. Now there will be how many states that will depend upon two S plus 1 provided L is greater than S, or 2L plus 1 if L is less than S. So whichever is greater, whichever is less, that multiplicity of that angular momentum should be taken. So let's start with an example. Suppose we have been given that there is a 2-electron system in an excited state, and one of the electron is in the D state and one electron is in the F state. So we've been asked to find out the values of L and J. So if it's in the D state, this will correspond to L is equal to 2 and L is equal to 3 for that state, because as you know, L is equal to 0 is for S, L is equal to 1 is for P, L is equal to 2 is for D, L is equal to 3 is for F. So that is why we take following values. So now we know these values, and since there are 2 electrons, we will have spin values 1 by 2 in both the cases, 1 by 2 and 1 by 2. Now the possible values of L will be the vectorial addition of these two. So it will be again 2 plus 3 minimum, 2 plus 3, 2 minus 3, or 3 minus 2, whatever we can put it. So 2 plus 3 is 5 and 3 minus 2 is 1. So we will include here the other values also. So 4, 3, 2. So this corresponds to all the L values. Similarly, we will have values of S as again S1 plus X2 vectorial addition. So it will be half and half. So it will be either 1 and it will be either 0. So we will have L and S values. Now For each L values, we will take up both the S values. That means now a way of representation of the states after del S coupling is 2s plus 1 Lj, and this is, as we have already told you, this is the multiplicity. So this is valid only if L is greater than S, and H will be changed to 2L plus 1 Lj if L is less than S. So, reading the previous problem, we will have L values as 5, 4, 3, 2, 1, and we will take first the S values as 1. So the J values will be, again we will have the vectorial addition of these two. So 5 plus 1 is 6, and 5 minus 1 is 4. So all the integers in between, 6 by 4. Similarly, 4 plus 1 is 5, and 4 minus 1 is 3, so 5, 4, 3. Again it should be 4, 3 and 2, 3, 2 and 1, and 2, 1 and 0. And the corresponding states. So in all this case, we will have the 2s plus 1 Lj value. So it happens to be, we get three states here corresponding to. So 2s plus 1 is 2. 2s plus 1 here is 2, and L here is 5, so this corresponds to H, so it will be 2H, and we'll have 3 states corresponding to 6, 5 and 4. 6, 5 and 4, there will be 3 states. So here again it will be G, and so again in the similar way we can have 2G, 5, 4 and 3, F, so again 2F, 4, 3, 2, and we will have D, oh sorry, extremely sorry, this should be 3, not 2. Sorry, it's 3 states. Since 2s plus 1 is s is 1, 4 plus 1 is 3. So it will be 3d, 3, 2, 1. And this corresponds to p, so 3p, 2, 1 and 0. So these are the all possible states after LS coupling. This is for S is equal to 1, so we have another set. We will do another set for S is equal to 0. So writing in the similar fashion, L has got values of 5, 4, 3, 2, 1, and S is having values 0, 0, 0, 0, 0. So here L is greater than S. Also, the values of J will be simply 5, 4, 3, 2, 1, and it will be a singlet state. We have no triplet state because 2s plus 1 is 1. So again, the states representation 2s plus 1 Lj. So this will be 1H5, 1G 4, 1F3, 1D2, and 1P1. Solve the states. Okay. Now, when there is a coupling between L and S, there is an angle between them. So the angle between L and S coupling is given as cos theta is equal to J into J plus 1 minus L into L plus 1 minus S into S plus 1 divided by 2 L into L plus 1 into S into S plus 1. This is the formula for the angle between L and J. So if there is an d electron and it's in one electron system, the possible values of angles have been asked. So using the formula for d is equal to 1, we'll have L is equal to 2, and since it's one electron system, we'll have S is equal to 1 by 2. So the possible values of J will be L plus S to L minus S. So that makes it 5 by 2 and 3 by 2. So it will be 2 states of J. So putting all the values of J. So for the first case, when so we will have two values of J is equal to 5 by 2 and 3 by 2. For J is equal to 5 by 2, the values of cos theta, considering L is equal to 2 and S is equal to 1 by 2, considering the value, it comes around, cos theta comes around root 2 by 3, which is 0.44, and the angle theta comes around as 42 degrees. And this is for taking J is equal to 5 by 2. If we take J is equal to 3 by 2, the value of cos theta is equal to 2, and this is equal to 1 by 2. The value of cos theta comes as equal to minus 1 by root 2. So again theta is 135 degrees. So these are the two angles, and we'll do one more problem. Is if there is a two electron system, it's called a PD system. It's 2 electrons. So S1 is equal to 1 by 2, and S2 is also equal to 1 by 2. The values of L for P, L is equal to 1. For D, L is equal to 2. So L1 we'll call it as 1, and L2 we'll call it as 2. So possible values of L are 1 plus 2 to 1 minus 2. 1 plus 2 is 3, 1 minus 2 is 1. 3 to 1 are the possible values of L, and possible values of S are again 1 and 0. So again, if we do the problem, so we have L value as 3 to 1. S values, will take the first one more case. So the values of J will be 3 plus 1 is 4, and 3 minus 1 is 2, so 4, 3, 2. For this case it will be 3, 2, 1, and 2, 1, 0, and for S it's for P, D, and F. So triplet. So 2s plus 1, 2s plus 1 Lj value, the states will be 3 F 4 3 2, 3D 3 2 1, and 3P 2 1 0, and for L is equal to 3 2 1 and S is equal to 0 0 0, values of J will be simply 3 2 1, and it will be our singlets. So it will be 1 F 1F3, 1 D3, 1 D2, and 1 P1. So these are the singlets. So this is how you write the different states of the telescope.